Okay, so we are in chapter 6, finishing chapter 6 this week, today on Wednesday, and then we'll start with chapter 8. Chapter 8, it's not that bad, but chapter 9 is the easiest. It's the easiest chapter ever because it's just formulas. It deals with formulas only, gases, laws, or gas formula. We'll talk about this. As I said, it's more or less physics. If you have taken physics, then you'll know about wave, about frequency of the wave, and then about the wavelength of the wave. So if I go here and show you how the wave is behaving, let's look at this in terms of the, so you can see from the top peak to the bottom, that's the height of the wave called amplitude. Amplitude is the from the height here. I hope I can take another color. So this is the height of the wave. Does not want to. Let's go back. So if you look at this, just to review from here to here, this is called the height of a wave, amplitude, correct? If I go further here up, from this peak to this peak, called lambda, wavelength, correct? And how it's repeating itself, so it go down, and it will repeat itself here somewhere. The repeating of the wave itself per time called frequency per time. It's 1/second, 1/second per time. So how it repeats itself, and if I want to just maybe look at it here, we take this one out. So this is the characteristics of any wave. The height of it, the length between two adjacent peaks, from the bottom to the peak, to the height, from the summit of the peak, that's amplitude or height, and then how it repeats itself, that's frequency. Just show you about this here. And if I want to get out of this, and so you can see how it repeats itself. When it repeats itself, that's frequency. So that's frequency. It repeats itself, correct? That's frequency. That's when redundancy per time, cycle per time, one cycle per time. A cycle is full from one peak to one peak. This is one cycle. That's a wavelength. Cycle from one peak to one peak. Just to be aware, somebody will ask about this. So now we have to deal with something called black body radiation. Black body or black hole, that's a real thing. That's a real thing. There's this big, huge objects in the universe called the vacuum machine. Any object near this big object will be sucked in. It's called the vacuum, or like a carbon vacuum. It's sucked in all the bodies inside, stars, meteoroids, suns. It's a huge, and it looks very dark, and there's for black holes. So that's real. But the black body radiation, that's theoretical. There's nothing there in the real life. It means it absorbs everything in. Absorb everything in, correct? All the light, and you know the light has 7 main colors, correct? 7 main colors. If your refraction of a light leads to what in a prism, you get 7 main colors there. So, and this black body here, it's all related to a theoretical body that's really absorbed every type of wavelength of the light. And that's not really true. That's just a theoretical thing. But the black hole, that's real. So, and and this one here, we'll say that's the perfect absorber of all type of wavelength and the perfect emitter of all type of wavelengths. So it takes everything in and then gives everything out, and that's almost impossible. And you can't find a body that can do that. Usually, it can absorb in some regions of the electromagnetic field, and it cannot absorb some other regions. Correct? So, and that's just a black body, and you can see those are spectral, depending on the temperature, 18,000 K Kelvin, 6,000 K, 4,000 K, and then you just subtract this one here from 273 to get your centigrade Celsius. You can see those temperatures are found where? In the sun or a very hot stars, correct? So this type of radiation, and depending on the temperature, will give you what different type of color. So you can see the different colors. That's what's happened if you have a piece of metal, for example, a piece of iron or any other metal, and you heat it, you will see the heat of this piece of iron. The iron, first of all, is dull gray, correct? Shiny gray or dull. And then it turn around to be yellow, then red. Then if you heat higher, higher, higher before it melts, you will see different color, yellow, blue. You will see that the piece of iron is being emits different type of wavelengths, correct? And that's what we call, we name this one not really a black body, but that can mimic a black body behavior depending on the temperature and what temperature is this object or this metal is subjected to. It will give you different type of color. Usually at lower temperature, things start red. If you heat any metal at lower temperature, 4,000, also 4,000 Kelvin minus 273, converted to centigrade Celsius, most of the metals are in this region. I mean, they'll start melting. So you see them, they start red. But if you touch them all the way up before they melt, you'll see they will give you different type of color. Which elements you think has the highest? The highest, which one? From all the elements here. Which is the metal? Has to be metal, correct? Which metal is give you the highest melting point ever? I mean, it takes a longer time to melt. So you can see even the red glowing. First, you can see glowing silver, then glowing red, and then maybe you see some other color coming out of it. Which one you think? Don't Google. Tell me which one. What do you think? Don't Google it. I know you can Google it. You tell me the answer. Tungsten. So the very, very small W tungsten. You know the lamp tungsten made of. The older one, not the new ones. The mercury, made of mercury and other elements. So W, this, and here what? Rhenium, W, and then thallium there. So W is tungsten, about 4,000 centigrade Celsius, about 3,000 something, 3,500. We said, sorry, just given and take 4,000. So 4,000 centigrade Celsius, that's a lot. And you can Google it, but that's the highest of all the metals we know. They melt at very high and then give you different type of radiation. So what type of nature is the light? Well, we talked about this, that the nature of the light can behave as a wave or can behave as what? As a particle. And you can see if the light going through, that means what? That's a wave. If I have a mirror here, cannot go through the mirror, correct? Because you have silver metal there, it will bounce out. So it's act like what? It acts like particle. So this is the same thing found in the electron. Electron moves with the speed of light, so it's a wave. But electrons can be attracted to a positive magnetic field or electromagnetic field, positive, they are negative. So they behave like particles, correct? They behave as particles. So the electrons, and then later on the photons of the light, those can behave as particles, or they can behave as wave. So Halloween is coming, correct? The end of October, in 2 weeks. So if I'm a wave, I'll be a ghost. So if I go to the wall, I can go through the wall, correct? I can go through this wall to the second one. So I'm a wave. I'm a ghost. Are you following me here? Makes sense? That's the way it is. If somebody out there has a transmittance and transmitting radio at FM or AM, so I can have a receiver here. I can hear the radio. So the radio going through the walls. Are you following me here? So that's a wave. But myself, I'm not wave. If I hit the wall, I'll bounce back. So that's particle. Particle cannot go through. It bounces back. So that's the difference between a particle and a wave. A wave can go through, like a Halloween ghost, right? Came out of the graveyard. From the graveyard, then go through buildings, through the walls. That's a wave. But then this wave, this dead body, whatever, dead soul, whatever, can go back, transform itself to a particle. So it can behave like a particle, can come and bother people, as they say in Halloween, correct? So that's the same thing with the light and electrons. They have this dual character. They behave as a wave. They can penetrate anything they go through, or they can behave, they can bounce out. That can be as particles. So, and that's what the light does. The light can reflect, can refract, can diffract. So all those are interference. So reflect, that's like a mirror. What's refract? Somebody will tell me what's refract? What's refract? So the reflection is bounce. You have a mirror, you put a light there, the light cannot go through the mirror, bounce back to you, right? That's the people can communicate in the camping. If they are lost or something, no GPS working, they can talk with the mirror. There's like, they can talk with certain, this is A, this is the mirror B, whatever, so they can communicate with the mirror, reflection of the sun, the light. So refraction, what's refraction? Refraction, somebody went fishing lately. If I see a fish here, should I put my whatever, my arrow or whatever, my tool to catch it like this, or I have to go further here? Where is the fish? Is the fish here in front of my eye, inside the water? No, the fish is not here. Actually, the fish is here. Why? Because refraction is the light going through two mediums. This is the air, and this is H2O. Two mediums. If the light goes through two mediums or more, then it will be refracted. Will be refracted. Refract means the light is broken. That virtually is broken. So it's the light going here, and then because of the medium density, it's not direct here. It goes this way. So always, whenever you are fishing, don't look at the fish here. You look at it, but it's not in front of your eyes. It's beyond your eyes because you are seeing the light inside the air. But inside H2O, another medium, it's far off. Are you following me here? That's called refraction. So reflection is coming out of a mirror. Diffraction is you have two sources of light or three or more, You put them together, they start interference with each other. You yourself will be confused which is which. That's happened if you have the light like laser. You have red laser, yellow laser, violet laser, different compound you are using to initiate those lasers. And then the light, a mixture of this interference, correct? All this light can do. So refractive is changing the medium. Reflection is hitting an opaque medium. It's coming bounce out of it. And diffraction is when you have more than source of light, they come interfere with each other. Too many lasers together, and then you see the color. It's not one. You see a mixture of colors in one. So all this is behavior of the light being away, but the light can be as particle, and that's what you see when you enter the elevator. There's a photocell. You see a beam coming through. If you put your hand on this beam or put Scotch tape, the elevator will remain open and nobody can get this elevator up. However, suppose your elevator is in the 10th floor and you want to make a trap for other people not to use it, just see the beam where it's coming, put Scotch tape on the beam going through, it's open. No electrical current going through, and the door is open, the elevator will not move anywhere. So they have to call somebody to come and fix the problem, to take the Scotch tape out. But don't do it though. But that's the way it is. This is a photocell, which is in this drawing here. The photocell is hitting the cathode. That's a photocell source coming and hitting the cathode, the other side of the elevator. So you are not aiming the other side, the cathode, no, other side, no. You are aiming the source, you are aiming here, incoming photons. You'll see it, if you look at it, a red line, red radiation going through. That's a laser, photons coming through the cathode. When they come there doing this, they kick out of the cathode some electrons. Electrons are moving, and therefore the cell is closed, and therefore the door is closed. You just prevent these incoming photons from hitting the cathode. Guess what? The door will be open and the elevator will never work, because the safety rule will prevent the elevator to go up with the door open. Can't. Some people they put their hands. Well, if you are behaving a little bit, to do some damage to other people living with you in an apartment complex, like 5-floor apartment, so just put Scotch tape on the incoming photons, and the elevator will come stuck. Nobody can use the elevator that day unless they call maintenance to come and take this tape out, so the elevator will not go up. So that's the behavior proof that the light is what is a particle. It's bouncing out. It's hitting the cathode and it bounces out of the cathode, coming out as a photon and bounce out as electron. Correct? Coming out as a photon and then getting out photoelectrons. So photons coming in and coming out as photoelectrons, coming out as electrons to close the loop, to close the electrical circuit. And as you see, you don't have to memorize this, but at least you know that the total energy here is kinetic energy, this one here, right? So let me just, and binding energy. So you don't have to memorize this, but at least you will know that's the total energy of this photon incoming particle is both, because it's moving, correct? So it's kinetic energy and binding energy. So kinetic energy is very important, correct? Is the energy that this photoelectron possesses minus the binding energy, correct? So minus the binding have to know this, and nobody will ask you about this, but at least the light is acting like a particle. It bounces out, going in as a photon, going out as a photoelectron, right? So, and with the alkali metals are acting very well in this type of bouncing out as a photoelectron. So you have coming in, correct? Going out. So if you just prevent this one from coming in, the circuit will not be closed, will be open loop, and there will be no current going through, and there will be kinetic energy will be zero because nothing is moving. So come the whole photon will come here and stops here. It's not moving anywhere, correct? Because there is no more photoelectron coming in. So here is just to show you how to calculate. We have a copper as a metal, correct? And this copper here is bombarded with the high energy, correct? Electrons, and then it's emitting X-ray. Calculate the energy in joules associated with this photon. If the wavelength given of X-ray is this, the wavelength of the X-ray. Well, you know that the energy is multiply is Planck constant. Planck is a scientist worked on this area for a long time, and multiply by the frequency of light. The frequency of light is this. The speed of light divided by its wavelength. The wavelength is given to you, correct? The speed of light is always 3·10⁸ meter per second. This is the speed of light. This is c. And the Planck constant is this one here. This is h, which is called Planck. Here, let me just Planck constant. So, and it has the value 6.63 10⁻34 joule per second. And then you divide the whole thing, this is divide here by the wavelength. Nanometer is, nano is 10⁻9. You take the n out, just replace it with the code value, which is 10⁻9 meter. And then you get joules per photons. Photons are particles, correct? So multiply it by the Avogadro's number, photon particles per mole. It will be the photon cancel with the photons here, and it will be megajoules per mole, megajoules per mole. And you can see here, you can compare the energy of UV light with 200 nanometer, give you this, if you can calculate this. And the light of the red is this one here. And I think I gave you the idea how to look at the whole thing here. Let me just show you here. It's very important to know. Here it is. This is, you see, we cannot see, we see always our vision, the visible, from 400 nanometer electromagnetic spectra, 400 to 700. That's we can see. We cannot see UV. You cannot see the IR, infrared. You cannot see the red or under the infrared, under the red. We can see the ultraviolet. We cannot see those. Ultraviolet to the right, this is the red, we cannot see them. Now, there are some animals like owl. They have the opportunity to look even in the IR, correct? Now, there are some goggles used by the, you can buy them. It's a military, they call them military goggles, night goggles. But you can buy them, it's not really military. You can, those people are camping in the jungle or in the mountains or forest or whatever. They use them a lot, especially in the night. Some animals, they are blind, but the most unique one from all the animal is the owl. Owl is the only creation that can see beyond the 400 nanometer to 700 nanometer. That's I can see. I cannot see beyond IR, infrared, or ultraviolet. I cannot see. I can see all. As a human, we can see between 400, and that's you can see here. As you can see, that's what you can see here. That's our range. We cannot go beyond this. So this is our range here. Okay. So you can go up infrared or ultraviolet. We cannot see those. Right? We cannot see those. Therefore, some animals, they have the power to see in the night much better than any other animals or other creations. So you can remember the owl, your online assignment, correct? So you know the owl is the best, can exceed the 400. It can go below 100, 400. It can go above the 700. So the range is higher. So those can tell you about the wavelength, and the wavelength is always opposite of the energy, correct? Guys, here. The energy is Planck constant multiplied by frequency, correct? That's the frequency. This one here is Planck constant multiplied by C over wavelength. This constant, speed of light, does not change, 3.0 10 to minus 8 meter per second. This Planck constant, correct? 10 to minus 24, 6.0 10 to minus 34 joule second. So those are constant, they don't change. So what is? The wavelength is the opposite of the energy. The higher the energy, the least wavelength. And you have to know this one sometimes comes in the ACS exam as a concept. Tell you of the relationship between the energy and the wavelength. Always give you multiple choices, and the answer is they are indirect proportional. Means if I have higher energy, then the wavelength will be low. If I have lower energy, then the wavelength will be high. And I can tell you that gamma and X-ray, they have the highest energy. X-ray can go through, correct? And you have X-ray and you have gamma rays. Those are very high in energy, but their wavelength is very small. So they have very short wavelength. So if you go like this, here, energy is very high, goes up. And lambda, the wavelength, goes low, and low, very short, right? And here, if you go up, the energy will go down, right? The wavelength will go up. Make sense, guys? So if you can see how the whole thing, and one of the here you can see the next one, you can see how you can calculate. Will give you the frequency, correct? You have the speed of light, you can transfer it into wavelength. Ask you about the wavelength. So the wavelength is the it is just the wavelength is speed of light divided by frequency. The frequency is given to you and ask you where is this in the range. So when you calculate, it came out to be 5.10 nanometer, 5.1012 nanometer. This is very high wavelength. So the energy will be what? Very high, correct? This is positive. And 10 minus 9 is so 10 plus 3. If you 10 minus 9, nano is 10 minus 9 multiplied by 10 minus 3. So it came out to be the range of it is radio frequency. correct? So radio frequency. So the energy itself there is very, very small. The energy is small. So from this, you can always look at the frequency, at the wavelength. Wavelength is always opposite of the energy itself. So, and you can see the radio are here. So see here, let me just get this one here. So here is wavelength up, correct? That's what we have seen, up. Energy is down. So the microwave, the radio wave, they have high wavelength. They can transfer, even if you have short wave, radio can transfer from one country to one country, correct? Through the space. Wavelength is very high, so they can transfer very far away. But gamma and here, energy is very high. Correct? Wavelength is low. So, and this is really very good, because if the X-ray is can go transfer far away, can do a lot of damage. So X-ray is just very local, can go through a body and then just be absorbed by whatever material is lead or something. So it has very short wavelength. So please we now here's the same thing here. We have Broglie. Broglie is a French physicist, and he worked with same thing with time of Planck, and all those scientists, they worked on this. Then Einstein came and then put the whole thing together as a law. So the wavelength here given to you. Now we are doing what? We are doing U in mass per second. This is the speed here. And we have m mass, and then U is the speed. So we have two. Berkeley had introduced, correct? So introduced here, look at this, guys. That's the wavelength itself. That's Planck constant, correct? That's the value of 6.6, 10 to minus 24 joule second. But now Berkeley has introduced the mass of the particle. That's the mass, and then the speed. So in his law, so you might put this one in our formula. So it does not come that much, but at least if you have a concept, right, will give you a lot of, you know, they give you this one here, C, divided by the frequency, and will give you this. This one here is Planck constant mass multiplied by U or V. V is the speed. V is the speed, not the volume, speed. So velocity or speed. So you can see, depending on what the question is, multiple choice, you have to differentiate between those two laws. Just put this one aside as a formula. I have not seen the Berkeley question that much. I did not see it that much asked, but this one is almost in every exam. So this one is in every exam is asked. Concept or calculation, concept or calculation. Here they give you what's the Berkeley wavelength in nanometer, give you the speed is this, correct? Then give you electron, so you know the mass of electron. So this is the speed. This is the mass of the electron. This is Planck constant. So you divide, here is divide. So divide the Planck constant with the mass of the electron and and here is the speed of the electron, correct? So I did mention that the speed of the electron is really speed of light. If you look at this, the speed of light is as you see before. What's the speed of light? Somebody will tell me. We did some examples here. This is 3.10 to minus 8, and this is 2.10 minus 8. This is close to the electron moving around the nucleus with the speed of light. There's no difference between 2 and 3. They are the same thing, but the same power, 10 power 8. So now, element from the sun. Well, helium was discovered in 2 occasions. One time is radiation coming from the sun, correct, in 1868. And then CHEM is from the part of mineral uranium. So from the alpha decay came out the as I said, came out the helium. So alpha decay. Let me just alpha decay. Alpha decay is, here it is. Alpha decay is helium. So this is atomic mass is 4, and atomic number is 2. And uranium is atomic mass is 235. That goes into the atomic nuclear plant, using atomic for electricity or for atomic bombs, either or, for both, for peaceful or war stuff, for both them. And its atomic mass is 90. So when it starts decaying, it decays to give you helium, was discovered by William Ramsey, and give you an X. So this is 90, will be what? 90 minus 2 will be 88, correct? 88, that's the 88 atomic number. And this is 4, 2, 3, 1. When uranium with the atomic mass 235, with atomic number 90, atomic mass 235, decay, radiation naturally. Nobody is really interfering. It goes by itself. So it gives us the helium plus an element with 88. So you can see what element is in 88. So 88, you can look. It is. Let me just tell you what the 88 is. We have the, I think we have the periodic table here. I don't want to lose this one here, so. Anyway, so look at the element 88, and this is the atomic mass of it. So the idea is helium all the time, when there is radiation for uranium, will come out as a byproduct. So that was the discovery of helium. Besides, it was discovered in the electromagnetic spectra comes out or came out from the sun itself. So we have the table now. So is element with atomic number. Those are lactanide 88. That's before uranium. Uranium is there. If you look at the uranium there, so this is coming. Those uranium in the that will be thorium, Th. So this is element with atomic number 88. I can't see very well. So 90, and it's 28. It will be, I think, 90 plus 2 is 88. Atomic number 88. So it says vtable.com. So not radium 86. So this one is 90. So it goes to uranium is 90, correct? So what we did, it should be 92, not 90. 92 is uranium, and it should be 90. So it's thorium, TH. So uranium is 92, 235. That's the isotope that's used mostly. But it has another isotope, very stable, 238. 238. So 238, another one, 235. So it goes back to thorium. So and helium. So helium is used. Just put this one here. Have it there for future use. So, and you can see this hydrogen. Hydrogen has 3 spectra, 1 red and 2 violet. So it has 1 red and 1 is a little bit bluish. Here it is. You can see the range here. So you can see it has a red, this area, and it has this one in this area, and it has this one here in this area. So it has 3 unique type of line or emission. So let me ask you, what's the difference if somebody will ask you, what's the difference between between emission and absorption? We have to know here, I'll go back here, emission and it is. So I want to know what's the difference between, those are emission lines. All those are called emission. Those called emission. So if I have an electron goes, this is level, so this energy level, say 3, correct? And this is level 5, n equal 5. So now this electron here goes from here, start here, then it goes up to here. So from here, this is called initial state, and this the other one called final state. So it disappears from here, so it stays here. So going from lower to higher, this process called this process here, this process going up, staying up, called absorption. Called what? Absorption. Absorption. So electrons goes from lower to lower to higher. That's called absorption. Now, if I reverse this one here, the electron there in this level feels anxious. I mean, literally means this is not my level I started with. This is a very awkward position I am putting in. Somebody put energy in my system, so I was raised to higher. So I don't like this. So what's happened is this electron here, so no, I want to go back. So now going back here, this called emission. Called what? Emission. So the called what? Emission. So electrons, and then when going back, whatever energy was causing this electron to go up, it will be given off. So this here, this electrons here will be given as photons, energy here, back. So those photons, you can see they are coming from the fact that electrons is pushed by incoming energy here, the photon raising this electron to higher level of energy, correct? And therefore the electrons, they don't like it because they feel like we have a lot of energy inside, we pushed out of our place, we want to go back to our original place, we have to give out this as a photon. It's called emission. And if you look, if I give you the whole thing here, this is the nucleus here, correct? So this is the first energy level. Talk about this. This is the second, n equal 2. Those are really sphere, but I'm just trying to write them here. This is 2, and this is n equal 3, and so on. So we have 7 period, so it goes up to n equals 7. Now, what's the end value of 7? It's infinite number, depending on future what this periodic table might be expanded, and we have more than 7 periods. So the periods, we have 7 periods, we have 7 energy levels. Starting from number 1, very close to the nucleus, and it goes up to 7. Why we stop to 7? Because our periodic table till now stops at 7th period. Now, does it mean there is no other period in the future? It depends on technology, it depends on other planets, meteoroids hitting the Earth, and we can discover new elements. There might be another period, 8th period, for example, or 9th period. We'll keep it to the future, but the value of n goes from n. That's the level here, from not 0, from 1. Start from 1. Near the nucleus, goes all the way to infinite number. So it goes from 1 to infinite. So depending on technology we will have in the future. So and if you look at this, sorry. Here, just an example of this. You see all those coming out. Yeah, we skipped to this, but let me show you that's again, this emission of hydrogen, 4. Hydrogen has 4, see here, different colors. And this is then the energy itself level. And this one here, you can see it. Can you see this? So those are n number 1 is close to the nucleus, goes n number 2, 3, 4, up to 7. Up to 7 because we have 7 beams. That's the energy level. And you can see the different colors. So different colors. Yeah. Greenish, violet, and the whole thing. So there is a law I want you to really put this one here. Put this one here in flashcards. You will need to go. So from higher to lower, that's emission. From lower to higher level, correct? That's called absorption. So absorption is a process by which electron is gaining energy, forcing it to go higher, correct? And it stays there for a while. It's not like it to stay for a while. Wants to anxious to go back to its original place. It goes back to the original place, so it has to emit, give away its gained energy. So, and that's what it says here. So I wanted to put this one here in your flashcards on a piece of paper. It's handy. that's his Rydberg constant, and it's given to you as is, this one here. And the principal quantum number, that's the energy level. Those are the orbital energies, orbitals around, correct, carrying out those electrons. And they possess, each level of those, it possesses definite amount of energy. So, and this is, N is, those are numbers here. Those are the number of principal quantum number, or just the orbital energies, correct? So as I said, I'm repeating myself, from lower to higher, absorption, from higher to lower, emission. So what causes the electron goes from lower to higher? Absorbing and incoming energy, kicking out this up because the energy coming in, this is here, it's absorbing this energy, going up. It's not like this, it's not stable. I want to go back. I want to go back to my original place. Whatever energy I absorb, give it out as a photon. Correct? And that can be by the, that's a Bohr model, but the formula is called Rydberg formula. This is Rydberg formula, but it's coming from the theory of the Bohr's. So if you look at this, look at this. This is the same way. It came out, and then it's giving out back its energy. So here goes from, they came out n equal 1. They all of them, they were in n equal 1. So hydrogen has only one electron. So they are not happy. They kicked out. They were kicked out. Electrons. It has two. It kicked out to the 1, 2, 3, 4. So 1 is or more than 4. This may be 5 coming. I don't know what from where. So coming out to its original place, it was in 1, first level. So it's emitting this. This is the same thing. The second. This is the third emission. This is the fourth emission. So if you have a picture of it, you'll see 4 of them. The violet, they don't really look very well. You cannot see them very well, but you can see the red and the blue, the light blue here. But the violet cannot be seen very well. So you can, but you can, if you have a magnifying glass, you can see the color here. So, and that's what really is all about, going down back to their original place. And by going to the original place, they will emit the energy they have. That's another example how to calculate. This is just a general thing. In the visible light, that's what we see. You can see the energy coming from the 6th, the emission from the 6th to the 2nd. You can see all our emission in this visible. That's what we can see. Here is infrared, and here is ultraviolet. And you can see the level from 6th to the 1st for ultraviolet, from the 5th to the 1st, from the 4th to the 1st, from the 3rd to the 1st, 2nd to the visible one. Starts with the second one, correct? Coming up from the 6th to the 2nd, from the 5th to the 2nd, the 4th to the 2nd, from the 3rd to the 2nd. The infrared is the same behavior, but they use number what? Higher in energy infrared, correct? Visible infrared, ultraviolet. So that's so you can see how they like. So, and then use this final formula. This is very important. It's coming last semester, coming last year, coming many years, this formula, Rydberg formula. So what we are looking for this, we can determine the energy here, and then from the energy, we can determine the wavelength, correct? So we can, even out of this, we can modify it, as you will see later on. We can calculate the wavelength of those transition. So this is the initial, this is F final, initial minus final, correct? Initial minus final. So a Rydberg constant, 2 point, is given to you here. you see, is here. 2.18 10 to minus 18, correct? And this is an example here. Give you this coming from the fifth state, from the fifth, that's final. This is drops from the fifth to the third. So it's negative. So we'll start initial, correct? Initial 5, and then final is 3. You square them and you calculate. This is your RH, correct? And then you do all your calculation. You calculate what? Calculate, oops, sorry. You calculate the whole energy here. Then you can multiply. Do this one here. You can calculate your what? Your wavelength. Why? Because you know this. You calculated this, the energy here. This is constant, 3.10 to minus 3.10 power 8 meter per second. This is the Planck constant, correct? And you multiply those together, you divide it by the amount of energy calculated, is already calculated here, correct? And you can determine the wavelength, correct? You can determine the wavelength. So here's another example. We talked about this. And here's the same thing here. Just we determine the wavelength. Here we have looked at the energy itself. Here we have in the core is the nucleus, and this is the probability to find the electron, correct? We cannot pinpoint where electron reside. It's impossible. Why? Because they are moving with the speed of light. If I move speed of light, then you cannot pinpoint where am I going, correct? Can you tell me where I'm going? No. I as big as move with the speed of light. Of course, human cannot do that. Our body cannot bear the amount of energy, tremendous energy will be evolved and will be not only barbecued, will be transferred into small tiny ashes. If we can move with the speed of light, our body will not bear it. Even the speed of sound. You go for 10, 20, or 100 times speed of sound, you cannot. If you drive a car with the speed of sound, correct? What will happen? The whole tires, the whole car will be flown in small pieces, and your body will be in small pieces as well. So the speed of light is impossible for a human to move with speed of light. It's just tremendous energy. We cannot be able to do it. Inside our body, the atoms of the elements inside our body, carbon, nitrogen, those atoms inside them, electrons are moving with the speed of light within the element itself, but a human cannot. So Schrödinger in 1926 came out to characterize the shape of this type of electron moving around the shape, their characteristics, how those electrons are moving around the nucleus. So Schrödinger in 1926, he came up with the mathematical equations. Believe it or not, the first day when I was in Germany in engineering chemistry, we have to learn, chemical engineering, we have to learn all the derivative, all the calculations of this guy here, Schrödinger, the German. That's about 8 or 9 or 10 pages you have to memorize how he came up with this solution. So the whole thing I'm talking now about these equations here, those are mathematical hypothesis, mathematical solution for mathematical equations. So somebody has seen that? No. So he came up with the very close description of those electrons, how they move inside the inside an atom. So this is an approximation. So you can't tell this is. I cannot find electrons moving around the nucleus. Remember when I told you about the idea? You hear has like, why? Because they are moving with the speed of light. You cannot tell the electron, oh, freeze here. I want to see your location. That can't happen. They are moving with the speed of light. So because their mass almost massless, correct? They have mass of 10 minus 24 grams. 10 minus 24 grams, just very, very, very tiny. So therefore, you cannot visualize how they move. So with these mathematical equations, he came with 4 of them. Here they are. Those 4 here. And let me just highlight them in red with the back. So those psi is a function that describes the situation of the electron density, not only one electron density around the nucleus itself. So let's look at this. It came out with N. N is energy level, correct? That's the energy near the nucleus. N equal 1, that's the first one. That's the orbital number 1 with its associated energy. So it's described the energy. L, correct? L is the orientation. Angular momentum is describing an angular momentum quantum number. The angular here describing the orientation of this electron density from the nucleus itself, correct? Like an angle where they are, where they can where we can find. That's a possibility to find them with this angle with the nucleus. M called magnetic and magnetic quantum number. That will give us the shape. So we have N is main principal quantum number, which gives you the amount of the energy of this electron density of electrons surrounding the nucleus. L is angular, give us angular quantum number, give us the orientation space of this electron density. M is magnetic, give us the shape. MS give us the rotation of this electron density. This is the nucleus, and then the electron density, bunch of them moving. If this clockwise, that will be designated plus half, plus 1/2, plus half. If it's counterclockwise, that's minus half. So this is what's really happening. So now L, we know that's L, we have 7 periods. N will have 7, but the value of N can go to infinite number, depending on technology. In the future, we might have more than 7 periods, correct? That's number of the period, or the number of the energy those electron density have in this energy level. So, or periods. So then L is to give us what? Will give us the orientation, correct? Will give us the orientation. L can have the value. So if N is 1, that's the first level. So we have the value, L will be 0. Always L from N minus 1. L will be N minus 1. Then you have the ML, which is very important, correct? If we have N2, then we have how many? We have 2. 2 means N minus 1 is 0. N minus 2 is 1. Correct? And we have 0. So two cases for L. And now, correct? And the L here will give you the type of the shape. So L equals 0, then you have S orbital, correct? That will give you the naming of this with the angular quantum number. So it give you the correct. So then you have S orbital, L equal 1, then you have P orbital, L equal 2, you have D orbital, L equal 3, F orbital. Shape of the volume or space or the density of electrons, correct, around the nucleus. So let's look at this. Fusion came with the N. This is N, give us what? Distance of electron from the nucleus. This is 1s, this is 2s, this is 3s. N equal 1, energy level 1, that's period 1. N 2s, that's period number 2. That's 3s is period number 3, and it goes all the way to s to n equals 7. 7 period we have in the periodic table. As I said, it can go beyond this. Yes, it can go infinite numbers. So it'll give us the distance of electron from nucleus, but not really the distance per se. It gives us the energy itself of this electron density spinning around the nucleus. So n, principal quantum number, which is given the distance, which is really the energy of the orbitals of this the electron density is found in. Correct. So here just give you the how the shape now. So the shape, that's the n, magnetic number. Angular give you the orbital designation, orientation in space. But the m will give you the shape. The s is spherical. The p orbital is what? Is dumbbell. The 3 orbital, very complicated dumbbell. So let me go back. L is angular quantum number, will give you the orientation in space, which will give you really the orbital designation. Then you'll have the magnetic, will give you the shape designation. This is spherical, so the electron density is spherical, works like spherical. The dumbbell here is the nucleus. They go like this. That's x-axis, or go z-axis. They move around the nucleus, or they come towards me, moving. Correct. That will be your y-axis. Now, if you look at this, just to let you know, this is the nucleus here, guys. This is the nucleus. This is the nucleus. All this, the coordinate 0, 0, 0 in 3D. That's our nucleus. Correct. And those orbital electron density of bunch of electrons are moving around the nucleus. Right. So it is, guys. And if you look at this, this is just the s orbital. L equals 0. That will be s orbital. This is the orientation. The angular momentum gives us the orientation. Now, this shape here is magnetic. Principal quantum will give you the shape. S orbital always, electron density will move in a spherical shape. Spherical. So S orbital from L, S equals 0, L equals 0. We have S orbital. That's L. But then the M, magnetic principal quantum number, will give us their shape is spherical. They have to. This is the S. When we have the angular has equal 2, then we have, or this will equal 1, that's p orbital. How they behave, they move around the nucleus. The nucleus is in the 0. Your 0 is your nucleus here somewhere. That's your 0 here. That's your 0 here, 0 here. That's the nucleus. That's your 0 here. That's your 0 here. So L equal 1, angular principal quantum number, means you don't have to memorize this. That will not come in the exam or anywhere. But at least you can see Schrödinger came out with the mathematical model. That's not true. Nobody has seen this. But this is the mathematical calculation of this. So that's the b orbitals. Correct? L equal 1. This is called dumbbell. Called what? Dumbbell. So it is dumb and dumbbell. 2 words. It's a bell, but it's dumb. So I'm sorry for that, but that's the definition of it. So then we have the d orbital is more complex. You can see it's complex dumbbell. So this is, if I look, this is complex. complex dumb. This is very complex dumbbell, and there are 5 of them, and you can see how complex they are. And in the middle, that's your nucleus, your nucleus, your nucleus, nucleus, and nucleus. So it's very hard to do the 3D motion with the 2Ds. That's 2D. So if I have this the nucleus, so they move like this, then they come like this, come back, then they go here, back, then. So it's very hard. So they move as electron density with the motion is very hard to visualize, very complex. The 7 has 7. That's L equal 3, then you have 7 orbitals there, and it's very, very complex. And you can look it in our ebook, it's inside, but at least you can see how complex is this behavior of the. So here it is. Now this is orientation. ML is magnetic. Magnetic give you what? Give you the shape and the number of the -1, 0, +1. So L equal 1, correct? That's p orbital. ML will be, and you look, if p orbital has how many? It has 3. It has 3 orbitals, suborbitals, 1, 2, and 3. D equal 2, then you have D. D have 5. 1, 2, 3, 4, and 5. Correct? So this is just to show you how is that's the p orbital with 2 second level, n equal 2. So you see how the whole thing is. This is a dumbbell, not a complex one. But then if you go for higher, n, that would be 5. This is d orbital. So you can see the difference how d orbitals are very, very complex. And those are all the orbitals. Nobody will ask you, but at least you will know. The last one here, Schrödinger said spinning, rotation around the nucleus. You have counterclockwise, it is +½ given designation +½ clockwise, or counterclockwise -½ So this is called the spin quantum number. So now we have 2 things controlling those electrons filling in those electrons. 2 things. One called Pauli exclusion principle, and the second one called Hund's rule. So 2. This is number 1. Here, let me just. This is. Oops, sorry. This is number 1. How those electrons are filling those n orbitals, the orbitals themselves. This is Pauli exclusion principle. And the second one, although it come late, but we have to know, it's here. Hund's rule. So something called Hund's rule. Yeah, here it is. This one here called Hund's rule. So how many we have? We have 2 rules are governing the filling those electrons. What are they? Well, we have 1 minute. I'll talk just talking here. Pauli says its rule or law, maximum occupation of any orbital has to be 2 electrons, cannot exceed 2. And those 2 electrons, they have condition on them. They have to have different spin. One will spin clockwise, the other one has to spin counterclockwise. So Pauli is maximum 2 of any orbital, maximum 2. They have to have different spin. The other one, Hund's rule, said, okay, they have 2, but when you enter them inside the, like 2 shuttles coming, two airplanes coming in at the same time, they have to come singly, each one by itself, and parallel to each other, not like this behind each other. No, parallel to each other means they have to have the same spin. Up, 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 or down, 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 down. You feel first all the ups, and then when all the ups electrons are spinning clockwise, then you go for counterclockwise. So I'll stop here, and then we'll come back and look at those two rules to fill in electrons. Thank you very much. So